Okay, we're going to talk about population dynamics with these cute little critters, rabbits, order Lagomorpha. They are really cute mammals, very unlike any other mammal. Rabbits and hares are distinctly different from rodents and other mammals. As you might remember in the experiment, the experimenters put a whole bunch of rabbits in this enclosed area where there was no emigration or immigration, and they tracked the number of female rabbits in the field over 10 years. So we're going to look at the data and see what happened. Okay, so they tracked rabbit populations for 10 years, and that's what the x-axis is the years, and the y-axis is density, number per hectare of just females. They didn't really care about males because it's really the females that they track for population and potential reproductive ability of the population. All right, one of the things you'll notice is that they have it as two demographics. They've got the old rabbits in the green and the young rabbits represented in the purple. And if you think about it, when we look at this, it looks like the population kind of shows this rise and then a fall and then a rise and then a fall. So they're sort of seeing the classic population cycles that we see in many small mammal species. And the other thing that's kind of interesting ecologically is that ecologists have a concept for population dynamics. And one of the concepts that they have is, let's see if I can actually make this work. Where am I? There I am. This idea of carrying capacity. And that is the notion that there's a certain amount of in the population that can be held by the environment. Like, what is the total number of wolves that we can have in the state of Wisconsin, given the resources available? And so ecologists think about population dynamics, and we'll talk more about sort of measuring population dynamics later. But they think about this idea that there's a certain sort of imaginary number of individuals that the environment can uphold, withstand, or upkeep. And now, interestingly, the concept of carrying capacity is represented by the letter K. Yeah, I know, it's kind of silly, but that's what they do. So when we think about carrying capacity here, looking at this graph, can you make a prediction of what you think carrying capacity is? So I'll wait a second while you write a number down, what you think the carrying capacity for this population is, or this environment. I would predict that the carrying capacity for this population is around that, 17. Now you might say, wait a minute, Wagner, why didn't you go way up here? Because that's the most it could ever have in the population. Well, carrying capacity often gets exceeded by population growth, and when it exceeds it, it gets yanked back down, and then it takes some time delays to recover, and then sometimes it goes past it again, and then it gets yanked back down. I don't know if you've ever driven a boat. When you were first time you ever drive a boat, that's often what you do. You make a correction and you pull the boat back, and then you make a correction, and you end up sort of weaving down the lake. Well, populations do the same thing. They overshoot K, and then they get pulled back down, and then they rise again and often overshoot. So I would predict that K is around, I don't know, what, 18 or so. And you'll also notice that the young rabbits too are also showing that sort of cycling up and down and up. That sort of mirrors the older rabbits as well. All right. All right. So this is a series of graphs we're going to be looking at, and let's orient ourselves to them first because they're kind of unusual in that they have error bars going both in the x direction and in the y direction. So on these graphs, the x is always the same. It's the population density of females per hectare. And you'll notice that when they took measurements of the various variables like the number of offspring or the number of litters, there was different densities of females at that time. So that's why you have variation on the x-axis and variation on the y-axis. Now, the first thing you'll notice is we have a very strong, what we call an inverse density dependence, which means that we saw this before with the fish, in that increasing densities of the female results in a decrease in the number of offspring that the female produce. And this relationship is pretty strong. Get rid of this random red line there. And you'll notice that the slope is not zero, significantly different from zero. P-value is less than 0.05, so it's not a zero slope. In other words, not just flat. And the relationship is pretty strong. About 60% of the variation in offspring produced is explained by the number of rabbits that you have in the environment at that time. So female density has a significant impact on the number of offspring produced. Also, we see that that's true for the number of litters that the female can produce in her lifetime. So this female, under high density situations, was only able to make, only able to make about just over 2 litters, where if a female finds herself in a very low density situation, they're making over 3 litters in their per female. So you can definitely see that the density of females negatively impacts both how many litters they can produce and how many offspring there are ultimately from those females. Yeah, so just to put a point on it, there's about a 65% decrease in the number of rabbits born when the population density doubles. So double the population and you more than half the reproductive output. Now we're going to look at 3 graphs that look quite different than the first ones, and you'll also notice that we still have the same x-axis. We're just looking at how changes in female density influences the other factors. Here, what do we have? We have the litter size per female, recognizing that she can have multiple litters in that year. Or cycle. So one of the things you'll notice is that there is basically no relationship, right? The p-value is above 0.05, so the relationship here is not different from a zero slope. In other words, you change the number of females out there, the litter size, how many babies are they given birth to, stays the same. So you can see they prioritize, I'm going to make 3 to 4 offspring, regardless of how many, if there's a low density situation or high density situation. Now the second litter cycle is again not significantly different from zero, so it stays the same regardless, but you'll see they've now pumped out more babies than they did the first litter. So there's this idea that you're getting better at giving birth, but ultimately density has no impact on how many offspring you're producing on that second litter cycle. And then if you get a third litter cycle, again, no relationship. It's not different from zero. So what does this tell us? It seems counterintuitive in that the females, when they go to reproduce, produce a fixed litter size. You get that? And now they may change how often they can produce litters, but when they do reproduce, density doesn't seem to have an impact on the number of babies. Now, of course, we didn't talk about the quality of those babies. Remember, we looked at that with the fish when we looked at how much yolk they would put in per egg. But here we don't have that data. We just have how many offspring are you making. All right, this graph is an interesting graph because what we're looking at is how old is the female and how many offspring does she produce in a season. And you'll notice that this is a humped graph. In other words, that there's an optimal number of offspring that they can produce in a season, right? And it happens between 3 and 4 years of age. So as they're younger, they're getting better at producing offspring, but as they get older, they're decreasing their ability to produce offspring. So this tells us that for these animals, the rabbits, the 3 to 5 year age is the optimal age for which they can reproduce. They can produce the most offspring. So what we're looking here at is a little bit different. So the y-axis is looking at a change in female density and a change in the fecundity from one season to the next. So imagine you're in a world in which the number of rabbits that you live among decreases dramatically from this year to next. If that was the case, then you would have a negative change. So in other words, you're going into a world in which there are fewer rabbits around. If you're over here, you're going in a world where there's more and more rabbits from one season to the next. So you have increasing competition here, and you have decreasing competition at this part of the graph. And what you notice is what's the changes in the number of offspring that they produce. You can see that when they're in a world with less competition, not surprisingly, they have an increase in fecundity. When they are moving into a world of higher density with more competition, then all of a sudden we find that that's season 1 to season 2, they're actually going to produce fewer offspring. So this is the density, inverse density dependent effect of changes in density population having a negative impact on the rabbit's fecundity from one year to the next. So what this is telling us is that as the population increases, this has a negative impact on the female's ability to make offspring, so that the corresponding year there'll be fewer offspring being added to the population, which would cause the population to decline, which would then move the entire population in this direction. And as the population gets moved in this direction, the number of offspring produced increases, which then drives the population in this direction, which then pushes down the number of offspring being produced, which then you get this sort of cycle. Feedback loop, which creates a negative feedback loop. I should write that down. It's a negative feedback loop, which causes stability, right? A density dependent. It's a density dependent effects on fecundity. And this creates that sort of stability around K. It may overshoot it, but it gets pulled back down, and then it rises back up, and then it oscillates around the carrying capacity. Okay, we're going to shift gears, and this is an interesting story because we're looking at flowering plants. This white wall rocket, this little plant that grows on the ground. You can see it's pretty small, clustered in the environment. And the researchers wanted to know how the densities of these flowers influence each other. All right, so this is a new graph. Let's look at the axis. So the axis is this idea of nearest neighbor distance. Nearest neighbor distance, there it is. And what it is imagine you've got this little plant, and then you got another little plant, and you got another little plant. And so what you do, we do this in ecology actually, you take this plant and you're like, okay, let's measure the distance between you plant. Where is my cursor? Oh, there it is. Oh, yellow is a terrible color. Let's pick blue. So I'm going to measure the distance between you, and well, that's not near. And so I'll get this distance here, D, and I'll record it. Then I'll go, who's closest to you, right? Measuring, and then who's closest to you, and who's closest to you. And so we end up with a bunch of values for each individual and their nearest neighbor, okay? And if we think about it, if I said to you, oh, as you go smaller on nearest neighbor, right, down here, and these are plants that can't move, if I have a very small nearest neighbor, that means somebody's right next to me, right? And if they're right next to me, they're probably competing with me. So on small nearest neighbor distances, you would think, oh, that's going to be crowding and competition. Whereas of the big nearest neighbor distance, you would probably predict, oh, I'm out here by myself. I don't have to worry about my neighbors. I'm not having to deal with competition, right? Conceptually, that's what we would expect, given all the studies we've looked at so far. So here's the first thing they looked at, plant size. And they're measuring it by the number of flowers that the plant produces, just like you guys did in our little experiment with the Roundup resistant plants. We measure the number of flowers as a measurement of growth. If you did that, what would you predict? I think, why don't you make a sketch of what you think this graph would look like if competition was important. I'm going to give you a second. You can pause the video. All right, what do you think it's going to look like? I would predict you would think it looks like something like that. Very few competitors, I can grow really big. I'm starting to deal with competitive. Oh wait, I said it backwards, didn't I? Ha 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 ha. Good, I hope you said, no, Wagner, that's wrong. What you would expect, right, is that when there's nobody around, I can grow really big, and when I'm really crowded, I can't grow, and I would have some sort of relationship like that. Because I'm here, I'm doing competition, I'm fighting for resources, and I can't grow as well as when I'm out here all by myself with no competitors, right? That's kind of what we'd expect given what we've been learning about competition in the world. Let's see what the data says. So you can see, I noticed that the slide started showing the data while I was talking. And you can already see, look, there's no relationship between how well the plants grew and how crowded they were. So it's basically a zero slope, contrary to what we expected. Now, let's look at the next bit of data. We're looking at the proportion of setting seeds. How many babies did you make, right? That's what setting seeds are. So we're looking at, first we looked at how many flowers, then we wanted to say the proportion of capsules that you have that actually make seeds. And what you notice is that when they're really crowded, they almost have 100% success rate. And when they're really far apart, their capsules don't have a lot of seeds in them. This is, what do we call that? Inverse density dependence, right? This is contradiction to what we're used to thinking. They seem to do well when they've got a bunch of neighbors around. And we see that basically that pattern is followed with the mean seeds per pollinated capsule. So what we're seeing is that not only are they getting more of their capsules fully making seeds, but how many seeds are they producing? They're producing more seeds than when they're spread out. So the last graph is really kind of probably what you really want to know. How many friggin' babies did you make? They can make a lot of babies, right? 100,000. Wow. 10,000. This is a logarithmic graph, right? 100 to 1,000 to 10,000 to 100,000. And you'll notice, again, inverse density dependent. When they're crowded and close to each other, they do much better than when they're apart. Why is that? Now, if you've done your reading, you already know the answer. This graph just shows you that all three of those graphs feed into each other to give you that total number of seeds per plant. How many of the capsules have seeds in them, how many of them got pollinated, that sort of thing. All that combines together to the total seeds per plant. So what's happening? It goes back to what we talked about before. Plants rely on pollinators to help them get pollinated. I just noticed that that is not a bee, but in fact that's a fly, which also do pollinate as well. And you can see his rump is covered in pollen, I think. Anyway, so for these plants, being in close, dense proximity to each other, they are more likely to attract pollinators. And guess what? They're more likely to be fertilized, pollinated from a different plant than being pollinated by themselves. So that allows for more cross-fertilization, cross-pollination, and more likely to be pollinated. So for these plants, we find that being in high density with each other is actually a positive factor in their fitness, contrary to what we've been seeing in other systems. All right, that's it. Hope you, I'm sure you can read about the jack pines. I don't think I need to talk to you through that. You're smart enough to do that. Hope you have a good weekend. See you Monday.